Thank you. All right. Yeah, okay. I'll maybe just mention this again. Like breadth first is like BFS is breadth first, and it's also level order traversal. So it's like searching for one level first. Then when it completes the search for one level, then it goes to next until it's like finish all the levels. And here are some basic properties of like this BFS search. The time complexity is OM because like for the BFS we complete when we like search for all the nodes, and then N stands for the number of nodes. And for the space complexity, it's OB. So the B here stands for the maximum breadth. It will make more sense when we like look at the implementation of BFS here. So actually, let me show you an example here. So here and I have the implementation here. So BFS is actually a very like a special. Its implementation is quite unique because it's utilized the data structure queue. So in here on the first line, we can see that like BFS is actually like checking the root first because if like the tree doesn't have any nodes, it's like done, right? You don't want to keep checking. And then like it has this queue to record the root nodes. So in here, let me demonstrate it here by so in here we have like a queue that is recording the root. So currently the queue has the root node, which is A. And yeah, so I'm like doing the example of this tree here. And then we enter this while loop here. So like while the length of the queue is larger than 0. So currently like the queue has a length of 1. So yeah, the condition's met. Then we enter it. Then the current node it's like we're doing like queue pop the first node here. So here we have the current node to be A. And since like we'll queue pop the root node, queue is empty right now. Now we enter those two like if conditions that check like if the current node has like children or not. And in our case, A has like B on the left and C on the right. So we enter both if statements and we append B and C into our case. And yes. And then we enter the while loop again. So the length currently is 2. And we pop the queue again. Now the first node, the first element at queue is B. So get rid of B. And now the current node becomes C. Becomes B, sorry. And so like since current node is B, we want to check if it has any children or not. But in our case, it doesn't have any children, so it's down here. And but the length of queue is still larger than 0. So we enter the while loop again, and we remove the C from Q, and the current node becomes C, and we append C's children into the Q. Now C has D and E inside this Q. And now we like repeat those things again. So like the length of Q is always larger than 0. Then like the current node then becomes like D is pop first, so get rid of D first. Now it becomes D. And D has left children, so we append F into our Q. Now the length is still larger, then we get a pop E. Current becomes E. And E doesn't have any children, so we're done on this branch. Then we pop the last element. We pop the last node here, which is F, and current node becomes F. And yeah, so far we have like researched all the tree nodes in this tree, and notice that the queue size actually never is never larger than 2, because the queue here is only like taking the nodes on one level. So since in our case, like each level doesn't have like more than 2 tree nodes, so the size of queue never like exceeds the number of 2. So that's why the space complexity, which is the size of like queue in the implementation, is always the maximum breadth of the tree. Does this make sense to like everyone? Does anyone have like questions regarding this?
That was a
Okay.
really good walkthrough.
Okay, thank you. All right, then I can go to next. So yeah, so since like okay, I think that's all for BFS. So yeah, I'll go through actually like go through the BFS here. So remember, BFS is the breadth first search. So it starts like one level by one level. So like if we do a print statement in our BFS, it will print A first. So it will print A, then B, then C, then D, then E, and lastly F. Sorry. So yeah, this is like if we do a print statement inside the BFS, we want to print like every node that we encounter first time. Then the BFS will give us the such printouts. Okay. Then let's go dive into
So
DFS.
Shengan.
Yeah,
So it's left to right,
yeah. It's left
down,
to
like reading
yeah,
a book, right?
yeah, because in here in this implementation, it's calling like append current node left above like current node right. So because of this order, it's always left to right. But like for some people, they maybe like prefer right above left. And in those cases, it's right before left. But yeah, generally it's left to right. Yeah,
Got it. Thank you.
welcome. All right, then let's dive into DFS. Cool. So DFS is different BFS because of the name and yeah, because it's searching the depth first before it's like finished searching all the breadth. So depth first means like the tree is actually want to go dive into the not really the deepest level, but it wants to like search for the depth first before like it search all the breadth. Well, I hope this makes sense, but I will demonstrate an example later. So actually, like DFS is more complicated than BFS because for BFS, it has other name called like level order traversal. But for DFS, there are actually like 3 types of like traversal inside of it. And they are called like in-order traversal, pre-order traversal, and the post-order traversal. And the implementation are here. So like the difference is really like the sequence of I mean like the place of this print or the like functionality you want to place between like the function calls of like this root dot left and the root dot right. So if you place like the functionality, in our case it's a print here, between like the two like function calls, then it will be this will become like an in order. So yeah, I mean like the name is really like literal. So the in order is like in literally between like those two function calls. And the pre-order is actually like when you want to place your function calls before like when you want to place your functionality before like the two function calls. Yeah, so yeah, this is kind of like a easy way to memorize it. So a pre means like you want to place the functionality like before the function calls. And the post order is also following the same rule. It's just like placing the functionality after the function calls. So those 3 are all DFS, but like because like the order of the functionality, they act a little bit differently. So you need to keep in mind of that. And yeah, they have like a really good video to demonstrate like the printout of those three different DFS. So yeah, if you have time, definitely watch this. It's really helpful. Okay, now we can have an example over delete. Should I delete them? Okay, I think it's fine. Let's look at DFS here. So the implementation of DFS is really easy if you use recursion. So in here, yeah, I have this code block here. And I mean, like also for like in order and pre-order and post order, they all look like very same because yeah, DFS by recursion is really easy. You basically because like the when we use recursion, it will be the recursion is like keep calling until it reaches the base case, and as we can see here in this like implementation, the base case is checking like if the root is a none or not. Null means it's not a node. So we can go through this together here. So as start, okay. Let me write down this. So at the beginning, no, not you. All right. So at the beginning, our root is A, not dot A. Okay. God. Root equals A. All right. So at the beginning, our root is A. Now we enter the recursive call. The first one is calling like root.left. Then in this case, the root is B. And under B, it calls like DFS root.left again. So it's referring to B.left. But as we can see, like B here doesn't have any children. So what does root of B.left give us? It's none, right? So in this function call B.left, since like B.left is a none, the function call will return return nothing in this case. So like the branch of recursion is complete in this case. And it's also same for beta right. Beta right is none, so yeah, we doesn't do anything. I mean like there's nothing there, so we wrap it up. And now like when it wrapped up, it go back to B, and B is actually like the children of A. So like we go back to beginning. Sorry, I know this sounds a little bit abstract because recursion is not it's not really intuitive, but I hope it makes sense. So like when we go back to the root A, and at this moment we finish all the checkings on the left side, so the B side, and note that we actually like dive into the depth first before we dive into the level search. So yeah, I mean that's literally why it's called like depth first search. And now like on the right side, it's like we enter this A dot right because we finished A dot left already. Now A dot right give us C. Now we have C here, and the C is like in a new like DFS call, and C is not none. Then we call C's children, and C has D as the left children and E as the right children, but it will dive into the D first because it's depth first search. And the D, all right. And the D here has only the left children, so D will dive into its like the left children first. And F doesn't have any children, so F wrap it up. It doesn't do any it's like it finishes, it's done here. So it go back to its parent, which is D here. And the D already checks its left children, which is F. And the D doesn't have a right children. So D is also done. So D goes back to its parent, which is C. And the C here is done with the checking on D. And so C only needs to check its right child, sorry. And then it should be, now we check E. And E doesn't have any children, so it is also done. Then E go back to C. And now like C checks all the children. And now C is done. Then C go back to the A. And now the function is completely done. So if we do a print statement, well, I think I would do a let's do an in order example here. Well, let's actually do all three. In order, pre-order, and post-order. So let's say like we do a in order printout first. Then if we do an in order print here, in order, then the print should look like whoops. So the print should look, remember like in order prints like it's the left child first, then the parent node itself, then the right child. So that means like in our case, in order will print out B first because B is A's left child, and then A will be printed. And then we go to the right branch. So like C will not be printed out yet because like it's a range, it's not a node yet. So C will dive into its left branch first because like it's like remember it's like root dot left before like the functionality. So C will go to its left child, and the D also has children, so D cannot print anything yet. D will keep calling, and D goes to F. And since F doesn't have any children, F can finally do the print. Now we print F. Now, like F is done, then we go back to D. Then like since we are done with this root dot left part, we can finally print out the root itself. Now we print out D. And since D doesn't have a right child, it's done. Then we'll go back to C. And we can print out C here because the print statement is reached. Now we can go to the right, and the right is E, and E doesn't have any children, so E can print out itself. So if we do an in order printout, the printouts will look like this. Okay, any questions? Did this make sense? I'll take sounds as
Yes.
yeah. Okay, cool.
I wanted to ask you, Adam mentioned that you can solve this kind of a problem with a stack.
Yeah.
I can't figure out how to do that.
Oh, okay, that's a good question. I think like DFS is really easy, so I actually haven't checked the stack yet, but I will check it tonight, and I will demonstrate like this by using a stack tomorrow.
I will say recursion is probably the better way to go. I may have jumped the gun with the stack. I think one of the examples I shared uses a stack or mentions it. But Shannon, I think you're right that recursion is probably easier.
Yeah, for DFS I usually use recursion because definitely they are easier to write. And I don't know if the stack gives better performance, maybe the same. But yeah, I would recommend like you to use DFS when like the recursion when you want to use DFS. It's a lifesaver.
Okay, yeah, we figured it out for the max step, but yeah, when I didn't even know how to.
I mean,
Yeah.
I'll definitely check the stack version tonight, and if possible, maybe I can present that tomorrow.
Awesome, thank you so much.
Yeah. Nope. All right. Any other questions? Nope. All right, good. Then we can do another, okay, 425, good. So we can do pre-order print here. Okay, pre-order. Oh, not pre-order. All right. Actually, I think it'd be more fun if like anyone want to volunteer on this one? Does anyone want to try lead us on this one? Do a pre-order printout? Anyone? Okay, no. All right.
What do you mean by pre-order?
Pre-order. Okay, so remember. Okay, maybe I should like copy and paste this. If it makes things easier. Okay, pre-order. So remember, pre-order is a type of DFS. So because like the print statement is placed on a different line, in like in relation to like those two function call recursive calls, they actually like act differently. So in our case, I try to demonstrate that like if you do a in-order printout, it will give us this like printout. But if you do pre-order, the printout will be different. Yeah.
Okay.
And okay. Oh, hope this is a good idea. Okay, so here is the, let me structure this a little bit. Oh, come on. If root print. Okay, I hope this doesn't look too bad. So yeah, this is pre-order. Does anyone want to try this one? Okay, no one. All right, then I would do. Who? You want to try this?
I can if no one else. Well, sure.
Oh, okay. You want to try this?
Yeah. Okay.
Go for it.
Okay.
So if it's going to print the root first for everything, it would probably be A, and then it's going to go left, so B, and then right is C, and then I'm guessing that next it will go left, so it'll print B, and then
yes. Sorry.
It-
D. Yep. And then
B has nothing next to it, so it doesn't print anything for that, right? And it goes to C.
wait, sorry, like which one are you?
Oh, sorry. So it actually just jumps down to D next, and then
Yeah.
it's gonna print F.
Yep.
And then E. I see. Okay.
Yep.
That makes sense.
Yeah. So thank you, Kate, for demonstrating this. Yeah, you're doing a great job. So that's true. Yeah, since like a print line is placed before any of the like recursive calls, so whenever we reach to a new node, we want to print it out first. So remember, like when we do a DFS, we do depth first. Yeah, because it's called DFS. Yeah, we want to like go to left first. So it's the order is A, B, and B is done. Then we'll go back to A, but A is already printed. Then we'll go to C. C here. Now we go to the left of C. Now we have D. And now we go to the left of D. Now we have F. And then lastly, E. So yeah, thank you again, Kate. Does anyone have any questions regarding this? Okay, now we can do the last one, which is post order. Okay. Oh, I don't need this anymore. Post order. And any volunteer?
I'll do it.
Okay, let's do it, Frank.
Okay, so for post order, it would go I'm correct. It would go F.
Yep. Oh,
Yeah.
post order is a little bit tricky. Let me double check. B, C, A, T, D, F. Yep, you're right. It start with F.
And then it would be want to say.
What's the next one that is done with the check?
E.
Try again. So like
Okay.
when we reach F, F is done first because F doesn't have any children, right?
Right. So then
And
it'll
then
be F, then
go back to D.
D.
Yep, because D doesn't have any right children. So when D checks it's right, then D realize like D is done, then D can directly print. So we have D here, and now next.
Will be E.
Yep.
Then C,
Right.
then B.
Actually, left, right. Actually, I think B should be sorry. I think like B should be printed out first. B should be printed out first because like remember, we're doing like left before right. So at the beginning, yeah, I will
So it'll
demonstrate this
be-
again. Yeah, so B should be at the beginning,
Okay, so then B.
and we only have the last
D.
one, so it's A.
A.
Yeah. Yeah. I hope this is correct. Sorry, I'm also not really familiar. Adam, can you do a sanity check?
Yes, I'm in the same boat, being a little less familiar, and also, Shannon, you're doing an awesome job. Thank you for doing this. My brain is, I can be a good participant, but I probably wouldn't be a good leader for this afternoon. I think that is correct. I think
Okay.
you're right, because there's a Stack Overflow post I've been throwing in comments from because they describe it well. We go from the bottom up, we find the deepest node in the left subtree, and we print there. And then when we're done, we go to the right subtree as deep as we can, and then we print the roots. So I think that's correct, because we went as deep as we could left and we got B. And then we go as deep as we can to the right of A. But as soon as we get to C, I think we have to we check to the left and we go as deep as we can there, and we get to F. And then when we move up to D, and one way to think about this is like each node sort of becomes the root of its own little mini tree. Well, D, then we print D, and then we go up to C, but C has a right child, so we can go deeper and we print E, and then we come to C, and we've done everything we can with C, so we print that, and then we finally get to A and print that,
Okay.
which is definitely a little trickier.
Yeah, I agree. Anyway, yeah, thank you, Adam, and thank you, Frank. So does anyone have like any questions regarding this? If no,
Yeah, I have a question.
okay.
Yeah, so I'm just confused by this three-stage process. What is being accomplished in order, pre-order, post-order? What exactly is the result of this?
The result of this, so I mean, are you talking about like the application?
Yes.
So like so the difference is like because like based on the position of this like functionality call, you will receive like different results, right? So in practical situations, this can be quite useful based on like based on the problem you are having. So I cannot give a good example right now, but I'd say like to differentiate between those three is definitely going to be helpful for like some future problems you'll be encountering.
Yeah, I can't think of a good example off of the top of my head either. And the good news is this is not something you all will have to be applying in the immediate future. But as like a sort of made up example, this isn't a great one, but like a game like checkers or tic-tac-toe, like using a tree to sort of map out all the possible moves is one common way to write a program to play that game. And so if you imagine the deeper in the tree, like the more moves ahead where we're looking, and that post order search, that one gets you know, as deep as possible on the left and right away. So if we wanted to look further ahead in our moves for this game or something, maybe we want to use post order. And that's, as I said, it's a bit of a made up example, but hopefully it's better than nothing.
Okay, so we won't necessarily be using all those processes? order?
Not necessary. They are not very important, but they're worth to know.
Is it true? Also, are the in order, pre-order, and post order, are those each different types of DFS? Using it?
I think that's true. Like, so under DFS, they are all DFS, and DFS has 3 categories, if I'm not mistaken. So we have like 3 categories: in order, pre-order, and post order. Yeah,
I think so as well. And yeah, Andrew, to answer your question, I'd say like the critical information to take away from here is a basic understanding of like how depth first search works. And that there are multiple ways to implement it. So I wouldn't worry about like trying to master each of them, because the truth is like we're not really going to be coming back to the data structure stuff, though we are going to try to be giving you all some leak code problems to do every now and then to touch on this. But this is such fundamental stuff, whether it's in technical interviews or like knowledge that gets built on later in your career, that having like a degree of comfort with trees and like seeing the 2 main search strategies, like breadth first versus depth first search, is really valuable.
All right, thanks. Shengan,
Yep.
would you mind just briefly going back to the BFS diagram?
DFS diagram.
BFS.
Oh, BFS. Oh, oops. Diagram. You mean like diagram? You mean, do you want me to like go over this code here again?
Oh, no, it's okay. It's all right.
Oh, you mean you want this block here?
Yeah, that's
Okay,
it.
gotcha. I mean, if you want, I can send it in the Victor channel later
Yeah, if you
on.
could do that, that'd be great.
Yeah,
Thank you.
of course. All right, so everyone's good, right? Then we can proceed to the next one.
Frank's got a question.
Okay, all right, go ahead, Josh.
Um,
Okay. Sorry, I
so
thought Josh.
no, it's fine. So just to like
Mhm.
go off of Andrew's question, it's kind of like this knowledge base is basically kind of like what the article that was about. Like, we should know this, we should understand in general how it all works, but you know, realistically we may just have to reference this and as like how certain code bases work, as opposed to having to build something like this from the ground up.
Yeah, I think that's correct. Thank you for letting us know this.
Yeah.
Go over the first kind, just real quick,
Mhm.
just
You mean like in order?
yes, please.
Okay, so let's pull out the in order first. Oh god, in order is here. So in order is doing like the root left check first. So in this case, like when we have A, we go to B first, and B doesn't have a left, so B goes to for B it goes to this print. So we print B first. Now like B doesn't have a right, so we'll go back to A, and now A goes to, and now like since A is done with the left check, A print out itself. So we have A as next, and now A we go to like A's right. So we have C here. So C needs to check like its left branch first. So C go to D, and D needs to go to like left branch. Go to do this left check first. So D goes to F, and F doesn't have any left child, so F print out itself, and F is done because it also doesn't have any right child. So go back to D, and now we print out the D after F because D has done with its left check, and D doesn't have any right child, so D is done. Now we'll go back to C, and C is done with the left check, so C can print out itself. So then C do the last recursive call. C go to the right child, and E doesn't have any children, so E can print out itself, and that's the sequence. Is this
Thank
good? You're welcome. All right.
Hey,
Oh,
Shengan.
yep.
Are these methods pretty useful in searching matrices?
Matrices, I don't think so. Matrices are actually more complicated, but I cannot like guarantee that. Um, I think those methods are mostly used in, from my experience, they're mostly used in data structures. So yeah, lead code problems, and mostly for tree structures.
And actually, if I can jump in, Shannon,
Yep.
there's an article that's one of the assignments for today. That is a really good, and I'll throw it in the Victor channel as well as the Zoom Slack, and it's in the curriculum. It's a really good breakdown of when you actually do end up working with data structures in the industry by a software engineer at Uber. And I think that's a really good example of like real world use cases of this stuff. And, you know, not every job, and probably not in your first job, to be realistic, will you be using this, but to give you a sense of how this stuff does get used, and also why it's valuable, because it's sort of like, it's not necessarily like putting a cap on career growth, because plenty of people become senior engineers and leads and team leads, and they don't work with this stuff at all. But there are like certain kinds of work where it's more necessary.
Thank you, Adam. Okay, so
because I should have just said read the article.
Yep, definitely. Okay, so does anyone else have questions? No. Okay, I was thinking about like doing another tree example, but since we're not, we're short on time, maybe we should go to like the lead code problem, the maximum depth. Actually, like I think like some teams might solve this problem already. Does anyone want to like demonstrate their code?
I mean, me and Frank finished it with your help, so I can share that if you want.
Okay, yeah, cool. So do you want to share your screen?
Sure, yeah.
Okay, I'll stop sharing.
All right, you guys see my screen?
Yep.
Okay. So I guess the way that Shannon helped us with this one, and the way that I understand it now, first we checked if there was a root, or if the root was none, we just returned 0. It was the root node. And then we found the max step on the left and right by using recursion. So we took the max step of the root to the left by calling the max depth function on root.left. And then we found the max on the right by calling the function of the root.right. And then we just had to compare them to see which one was greater. So we returned the max of the left or the right, and then we added on one to add one for that root node, I think.
Yeah, that's great. Thank you for sharing. Okay. Now, I think it would be better for me to demonstrate this process by doing some drawings here. So, okay, in case someone hasn't read the instruction for this problem. So this problem is actually trying to find out the maximum depth for a tree, for a given tree. So the depth is defined as, you can treat it like a level. So let's take an example here. In this one, we have, let me annotate here. We have like 3 levels. The first level is this root node, and the second level contains this 9 and 20, and the third level has 15 and 7. So, and that's why when we call this max depth function for this tree here, the function should return a 3 as a result. Okay. Now we understand the instruction. Let's use a different example actually. Let's go back to my drawing here. So, maybe I should have the code out. Well, actually, like Anna, can you send the code to me in the chat? Okay, thank you. Add this a little bit. Okay. So here I will go through the implementation here, and hopefully it will make more sense to you. So this max depth function is actually a recursive function, because as we can see here, it's keep calling itself. And remember, for each recursive function, you need to have the base case. And let's think about like for this problem, what should be the base case? So like since like we want to search for the levels, then we definitely want to like check every node. And in order to check every node, we can use the concept that we just learned, DFS, right? So for DFS, the very usual base condition is like when it's like this. When like the given node is none, then we stop and start returning values. And then to make it more concrete, basically like when we reach to a end node or like a leaf node. So the definition of a leaf is like when the node doesn't have any children. And in this case, like B is a leaf node, F is a leaf node, and E is also a leaf node. So when we like reach to those leaf nodes and like B is calling like its non-children, it's like giving none as an input to max depths, then in those cases, they will return 0 because there's no more levels below those nodes. Now we understand this. Let's go to the recursive calls. So first, like Anna's team like calls the self max depth root left. So it's like the DFS call. It's traversing through the whole tree, and yeah, it's searching for the left depth first. Then go to the right and search for the most left depth. So it keeps going. This should be quite familiar from the DFS implementation I just gave. So in case you forgot, oh, I deleted it. Too bad. All right. But yeah, here like it's calling it like left, root dot left first, then root right. This is basically doing a DFS for the whole tree. So like something so this part is DFS search. But different from DFS, the return like we return an extra step in this like implementation. Because remember, once you return the maximum level, and then here like max left and max right are returning something. Self.max steps roots left and self.max steps roots right are returning something. And the value they're returning is actually like the orders. Should I say no, the levels actually. Or you can more intuitively, like they are returning like number of edges. So like let's take an example here. So when we start at A, and A is the root in the first recursive call, and A is not null, so we do not enter the base case. We do those calls first. So we call like max depth A dot left, and we go to B. And since B is entered first, now we check B, and B is not null, and B doesn't have any children. So like when we input B's left into this self.max steps, this actually will return 0 for us. So like when root is B, max left is 0. And does B have any right children? No. So like the base case check will also fail. Well, it's not fail, like, but it will return 0 for us. So we have like max left and max right for B. And so that means like B's left child and the left child, B doesn't have any children. So like there's no levels below B. I think you can understand like those return values like this. It's 0 because there are no more levels between like B, under B. So now like since B is finished with check, we go back to A. But remember like B actually has a connection between like itself and A. So the level here should actually be 1, not 0. And we want to like achieve this by like modifying the return value. So that's why we have this +1 here. Because like whenever we finish the like valid check, and if there is a connection, there is a like left connection, either left connection or like right connection, we want to add a 1 to indicate that there is a valid level existing here. Hope this makes sense. And the last step is this max. This max is very interesting, but it's not hard to understand because, oh God, doesn't work as intended. Okay, not like this. Oh, come on. All right, I give up. Okay, so this max left and max right makes sense when you like when we go to like A dot right. So in here, since we do this +1, so bear with me right now. We do not look at this max here. So but the value since it contains this 1 connection, the value returned by like A's left should be 1. But since we haven't checked like A's right, so let's assume we've already checked all those branches. So A got a return value from these branches by calling like self.max steps A.right. Now like as we can see, like this value is returning the number of connections. So like the max number of connections, or the maximum number of connections here is 2 because C, D, F. So we have 2 connections here. So the ideal like a return value here should be 2. Now it has 2 options here. Either it wants to accept the 1 connection on the left side, or it wants to select the 2 connections on the right. But we're doing this max steps, so we want to maximize our depth value. That's why we have this max function to do this for us. So in A's case, like max left is 1 and max right is 2. So like max select 2 for us, and we do 2 plus 1 equals 3. So the return value for max steps when we call the root A is actually 3. And this is correct because we have like 3 levels here, right? Oh, sorry, like I think this 1 plus 1. Yeah, it should be 3.
The
right?
number of edges, I think.
Okay.
We just count the edges.
Yeah. I think like it's a little bit on this, a little bit different on this one, because for this one it returns 3, but actually like number of edges on this one is 2.
Oh, interesting. I
Yeah.
may be wrong there.
I think like it does do a last. So this one it returns 0 for this one. So here it should be returning 1 on this one. And here it should be returning 2 for this one. D does return 0, 0. So this one 3. Oh, so I think on lastly, like when it returns at the end, when like A is done with the selection. Oh no. This doesn't make sense. We should not do this.
Well, isn't the recursive aspect of this that each node is going to return 1 until it's none and then it returns 0? So it's essentially just counting each node in our tree
Count.
and then just.
Oh yeah, you're correct. Yeah, thank you, Matthew. So yeah, you're right. Actually, like in here, like it's returning like 1 node. So yeah, sorry. Instead of like looking at the connection, you should be looking at the number of nodes. So for A, the selection should be actually between 1 and 3. Sorry, I thought it was previously counting the edges, but in fact, we should be like do the counting on the number of nodes. So in here, like it has like 3 nodes and maximum. So the selection is actually between like 3 and 1. And the A is the last node it wants to add to itself. So that's why we have 3 plus 1 equals 4 as the return value when we do the max steps on this tree. Okay, so does this example make sense? Does anyone have questions?
So that last return statement is just weighing the left and weighing the right and seeing which has a greater value.
Yep.
And then you just add 1 on top for node A.
Yeah, before further returning, because you want to add yourself into the party.
Cool.
Okay.
Add 1 for max left.
Sorry, Adam, can you repeat that?
In that return statement, does max left need a +1 as well?
I don't think so. Because like max left, if we look at this, it's like it's actually like correctly counting like the number of nodes on the left branch, because like it's returning like the correct value by doing this like +1. Actually, I think I would do a more.
Okay, I may just have misread that then.
Yeah, we just like Anna submitted and it works. So it's definitely right.
Got it. Thank you.
Yeah, you're welcome. Okay. Is everyone clear on this? If there's no questions, I think we can do stand down because it's already 5.
Yeah, perfect timing. Oh, I see. Okay, the +1 is outside the parentheses.
Yeah,
That's
sorry,
fair.
like I make it look a little bit messy.
No, this was awesome. And honestly, I clearly need to start using TL draw more. So this was great.
Okay, yeah, so in case you still have some problems, so tomorrow we'll have another session over data structure. So if you have questions, you can also ask in tomorrow's session. And I will stop sharing here.
And just hit stop record.
Oh yeah, definitely.
And I think